She's on mute here.
Hello, everyone. My name is Anna from APNIC, and I will be your MC. I hope you are all doing great, all happy and healthy. This is APNIC 50 Keynote and Technical Session 1. I'm going to spend the next minute to explain about the housekeeping. This is our first track for the technical session today, and we have a lineup of excellent speakers, so I hope you are all excited. Interaction is very much encouraged, so we want to hear your questions, your comments, and we would like to see photos of you participating on Twitter or Facebook using the hashtag APNIC50. I'd like to remind you to be mindful of the code of conduct, which is published at the conference website and in the chat room. If you want to ask a question or write a comment, you can either use the raise hand function in Zoom and you'll join the queue for voice question, or use the Q&A button in Zoom for text, and I will read your question or comment to the speaker. If you don't get the chance to ask your question, you can email conference@apnic.net and we'll forward the email to the speaker for you. Use Zoom chat for any questions you have that are not related to the presentations. More help is available on the conference website. I am now inviting Warwick Mitchell from ARNet, who will be moderating this session. So over to you, Warwick.
Okay.
Sorry, Warwick, we can't hear you.
Can you hear me now?
Yes, we can. Thanks,
Sorry,
Warwick.
my apologies. Sorry. I just wanted to say thank you and to Anna for the welcome, and welcome everybody to the technical session. The first speaker today is Alex Leung from Akamai, who's going to be talking to us about how Akamai worked with its customers and partners to avoid internet congestion whilst managing the COVID-19 pandemic traffic requirements. So over to you, Alex.
Hello, great. Let me share. Hello, everyone. My name is Alex Leung from Akamai Hong Kong office. I feel so privileged to use the Zoom APNIC 50 background and meet you guys virtually. Before I begin, is my voice level okay?
Yes, we can hear you clearly, Alex.
Great. And now I'm trying to share my screen. Great. Sure. Hello. Thanks again for Anna and Warwick's introduction. The title of my presentation is For Such a Time as This, How Akamai Works with our partners and customers to avoid internet congestions during the pandemic. Here's my photos showing I work from one of the beach in Hong Kong and one of the rock, a piece of rock on the beach serve as my table for my laptop, particularly useful during the time of social distancing. And here's my LinkedIn. Feel free to connect over that. And so as we start to see more and more people work from home or start doing their vacation in their home and even work from beach, we know the internet is no longer the same place. So that's why that's the main focus of my talk. Today, we will be talking about some of the important and remarkable characteristics of the internet traffic as observed on Akamai platform during the pandemic. And we seem to be seeing some new norm, and we believe the world's internet usage will be taking a permanently forward, and we'll show some traffic charts to explain why. And because media and gaming console customers represent a major portion of our traffic, so we'll be zoom into that and share some technique for trimming traffic volume or traffic peaks for those customers. And we'll also talk about some protocol level optimization that we have been doing even before the onset of the pandemic, which includes IPv6 and IPv4 dual stacking of contents, and also dynamically picking up the right TCP congestion control algorithm from machine learning. So let's look at some of the global figures on Akamai CDN platform that really shows the effect of the pandemic and also a change in the pattern of how people work and how people do their e-learning and do their online shopping. Globally, from end of February to end of March, we are seeing a 30% increase in the traffic on Akamai CDN. And to put that into perspective, organically, usually we are observing 3% organic growth on a typical month. So 30% is like a 10 months of growth all squeezed into a 1 month period. That shows a truly remarkable growth in a short span of time. And also year over year, on March 2020, the peak traffic is double of that compared to March 2019. And that's also a remarkable characteristic during the month of March, when major economies of the world are beginning to implement lockdown measure to reduce the spread of COVID-19. And the upcoming two traffic graphs will be zooming into two particular countries in the APJ. Firstly, I would like to show Malaysia's trend. Here you can see when the lockdown measures start to get introduced by the government of Malaysia, we see a surge in internet traffic, and that's sort of expected and follow a similar trend we observe in many other countries. When the government introduced lockdown measure, the community and the internet users in that country will start downloading mobile apps for say gaming, for movie watching, for doing commerce and shopping online, and for helping their kids to do e-learning online. So that explains a new level of traffic. But what might be worth pointing out is even after some relaxation of the government policy, the traffic level stays at a similar high level. And so it seems that the community of the internet users in Malaysia have got used to this new way of doing e-learning and online shopping and work from home. And even when there's a relaxation in the lockdown requirement, the habit continues. And for those who are interested at this sharp peak of traffic near May 15, and that's related to an online game sale introduced by one of our customers. Okay, now let's zoom into India. Here in India, we see a similar trend like the one we observe in Malaysia. That is, as soon as lockdown measure introduced, we see traffic jump, and that continues even when Unlock 1.0 has been announced. And one important thing we would like to point out that is traditionally the India traffic would be seeing spikes correlating to cricket games. For example, before the pandemic hit APJ or India in January the 19th, we can see these two peaks that correlate with the cricket match as part of the T20 series. So that shows the peak. Now, in around March, usually there would be India Premier League, IPL traffic showing similar spikes. However, due to the pandemic, IPL has been postponed to September this year. So that explains why you are no longer seeing similar cricket-related spikes during the month of February or March. However, once the lockdown measure introduced, you will be seeing the internet usage has been consistently high and comparable to the level of highly popular cricket matches. That really shows that the traffic surge since middle of March has been driven by an increase in internet usage due to the lockdown measure. Apart from the general internet usage, we would like to also take a look at the different types of traffic categories. And as we see people start working from home, there would be, we are seeing the trend of work from home users using corporate laptops to do their social networking or even gaming and movie watching. But what is remarkable when comparing March 9th to May 11th figure, there's a 5-fold jump in malware traffic. When this correlate with the fact that when the whole world is focused on one single issue, that's COVID-19, there are lots of phishing sites and malware sites trying to take advantage of that and attract users to fall into the trap and get infected by the malware. So as a CDN, the last thing we want to accelerate is malware. So we have stepped up our investment and deployment in cloud-based secure web gateway and also sandboxing technology for doing more in-depth traffic inspection in support of our enterprise customers who have lots of work from home users and needing malware filtering at the edge of the cloud. So this talk is about how we work with partners and customers to avoid internet congestion. So let's take a look at what is internet congestion. So the internet is not just one homogeneous cloud, but in fact it is a cloud that contains many clouds of autonomous system. So here you can see one internet users contacting the origin through the various autonomous systems. And when a lot of people get online, there could be congestions at some of the peering points between AS, right? And this is where Akamai can help as a CDN because we are replicating part of the customer origin to the edge cache servers in the autonomous system so that can reduce the need to go beyond the congested peering point to fetch the content. Now, however, there could still be some last mile congestions that CDN may not be able to solve. See here, when a lot of people work from home in the residential areas, the last mile service offered by CMTS or DSLAM, like everything under the sun, the DSLAM and CMTS, they do have a capacity limit. And when they're large scale work from home, that could hit that device limit and causing congestions at the last mile. So here's an analogy on how congestion can happen and what we can do to trim the traffic volume or the traffic peak to avoid that. So here it shows a pipe of internet with finite capacity, and the vertical axis is the bandwidth and the horizontal axis is the time. So when two big source of traffic are approaching each other, if the peaks are both having big peak and big volume, congestion can happen. Now, so there are two schools of thought to address that. One is to flatten the curve. To you still deliver the same amount of volume for, say, movie watching or e-learning, but you reduce the peak or of the shape of the traffic. So that helps to avoid a collision. Another school of thought is to try to use a novel way of encoding your object. Your object could be a video movie object. By using novel way to encode it, you can reduce the size of that video object, and that can also reduce the probability of traffic collisions. So a general challenge we heard from our media and gaming console customers during the pandemic is that they need to do more with less, and they need to figure out new ways and work with CDN and other delivery partners to reduce the volume of traffic being delivered and or the peak data rate. And at the bottom of the slide, you can see even various governments around the globe are asking the over-the-top media delivery companies to reduce their bit rate so that the internet can work for everybody and not just for the movie watching. So here we can see we are going to show highlight 3 ways to trim the traffic volume and the peak data rate. That one is involving change in the content encoding of the video object. The second one is change to the way we describe the video object in the HLS streaming manifest. The third way is about doing traffic throttling at the level of the CDN. So we have a demo page that shows demonstrate a movie playing, and you can see in this movie the top bit rate is 8 megabit per second, and it's also noteworthy to show that Akamai, just like any other CDN, normally we would support the movie being downloaded at a rate as fast as possible. So in this example, the download rate is over 100 megabit per second. So that's about 50 times of the movie speed rate. You divide by 134 by 8 megabit per second. Okay. So one technique is that we can do smarter encoding of the video object. This idea is called per title encoding or content aware encoding. Main idea is lies in one observation that you don't need a one size fits all bit rate ladder. Before per title encoding, the OTT industry has been using a 1 bit rate ladder for every movie. So be it animation or be it cartoon or action-packed thrillers or relatively speaking more static scenes in some romantic movies. So With per title encoding in this example, you can see sometimes a more optimized bitrate ladder can be arranged that can offer the same resolution and the same quality as shown by the peak signal to noise ratio on the y-axis. But the blue color bitrate ladder can offer for the same resolution, same quality, offering at a lower bitrate. So on average, we have customers seeing a 27% bitrate reduction. So that really reduce the volume of the traffic object. Now, so in this example, we are now doing the streaming of the same movie, but using content-aware encoding, and you see the top bitrate has been reduced from 8 megabit per second to 3.4 megabit per second. So even before the pandemic, the OTT industry have been working to do more with less. That they've been keep inventing next generation newer codecs. So everyone is quite familiar with the 17 years old H.264 AVC as the very common foundation for internet video streaming encoder codec. However, for the past 7 years, there are new, at least 2 new next generation codecs been available. One is H.265 and VP9. I would like to highlight the H.265 is now widely available in the Apple ecosystem, such as Apple TV and iPhone, and that offers a 50% reduction in bitrate savings compared to H.264. So now let's move on to another way to reduce the top bitrate. That is by removing it from the manifest object that describes the adaptive bitrate video object. So here, the yellow color, you can see that represent the top bitrate having about 8.4 megabit per second. So at the origin level or at the CDN level, we can in response to government requirements, we can temporarily hide the top bitrate by removing it from the manifest. So that can happen on the origin side. And some of our customers will also try to hide it from the player side. So for example, in the HTML5 ABR player, you can use JavaScript to do something like hide the bitrate and only allow playing bitrates that's less than certain threshold. Now, you can also do it at the CDN level. The CDN level will offer you flexibilities, such as allowing you to hide the top bitrate, say at certain time of the day, in responsible to certain geos government requirements, so that can help that nation for everyone to have a fair share of the internet bandwidth. So the next tactic will be doing CDN throttling. For CDN throttling, it does not reduce the volume of the video object. It's not using any advanced codec, so the video object is the same size. However, it reduces the traffic peak that helps to reduce the probability of congestion. So like the previous example I mentioned, usually CDN tends to deliver contents as fast as possible, like 15 times faster than the bit rate. However, during the pandemic, we do observe 2 legitimate needs to be balanced. Legitimate need number 1, for during social distancing, we do acknowledge gamers, video gamers want to do some socialization, despite the social distancing rules. They need to get themselves entertained. So with CDN throttling, we will reduce the speed of CDN download speed to say 3 to 5 times faster than the bit rate. So the gamer can still download the content they want, but it may take a little bit longer than usual. And on the other hand, we are trying to balance the legitimate need number 2, ensuring healthcare workers and first responders who are working hard to contain the COVID-19 pandemic to have continued access to the vital digital service that they need. So the detail of CDN throttling has been described in this blog. Now let's move on to some protocol level optimization that we have been doing. In this URL, it shows Akamai's IPv6 adoption visualization graph. So we particularly want to highlight 2 nations in the APNIC. That one is the Philippines, the other is Nepal. And you can see that with the onset of January 2020, there's been significant growth in the IPv6 adoption. And this sort of expected because during the pandemic, more internet users will be getting themselves online and getting themselves online for a longer time. And that certainly exacerbates the IPv4 address depletion problem. So we do expect to see more adoption of IPv6 and during the pandemic. And here, particularly for the nation of Nepal, you can read one of the APNIC blog about how world links in Nepal are deploying more IPv6. So why is IPv6 related to the probability of congestions? Here you can see that we have a network architecture diagram that shows usually the ISP and the mobile carrier, they support their IPv6 client by installing a carrier-grade NAT. That is the NAT624 device that helps to do the network address translation from IPv6 address space to the IPv4 address space. Now, imagine a piece of content that's existing in only IPv4 host. That could be, for example, a highly popular piece of content relating to cricket games, cricket matches. And if that piece of IPv4 only object all of a sudden becomes very popular, very hot in demand from that nation's IPv6 clients, and large number of IPv6 clients are trying to access that piece of content existing only in IPv4 host, then that carrier's NAT64 device will become constrained, will all of a sudden become a choke point of that carrier. So that's why Akamai and also APNIC, we have been promoting to avoid such bottleneck by dual stacking contents. By dual stacking means make that potentially highly popular content available in both IPv4 host and IPv6 host. This way, you can allow more direct access to that content through IPv6 network without bottlenecking the NAT64 device. So that's one protocol level optimization that's good to avoid congestion. Another protocol level optimization is helping every connection to pick the right TCP congestion control algorithm. Here it lists out the 5 congestion control algorithm that's currently supported by Akamai. You can see some familiar names such as Cubic, that's or BBR, that's inside the regular Linux kernel. And there's also some proprietary one that's invented within Akamai, such as QDK and Reno++. So from the traffic statistic we have been observing, we do have some numbers that we observed that shows you just cannot treat any particular CCA, congestion control algorithm, as a silver bullet. In other words, we do not observe any data to point to any CCA that being the silver bullet, that being the medicine that can solve, that can be the best choice for all types of connections. For example, in certain APJ cellular network, we observed the fast TCP CCA being the worst performing CCA. However, in certain fixed line network in APJ, the fast algorithm being the best performing. So what we are advocating and what we are doing among Akamai internally is we use machine learning to learn about what is the best and most suitable CCA for every connection, taking into account the AS number, the size of the video object, and there's a number of other signals that we will take into account and use machine learning to pick the right one. So that's the second protocol level optimization for congestion avoidance. So here's the summary of my sharing. There are multiple course of actions that can be taken to address over the top video traffic peak and volume, and that can be implemented at various stages of your delivery, be it server side, client side, or through CDN. And at the protocol level, dual stacking of contents can avoid the carrier grade NAT becoming the choke point. And we also advocate the use of machine learning for picking the right CCA for every connection. So there's some further reference slides and acknowledgement that you can refer to. Okay, that concludes my sharing today, and I will seek Warwick's help to see if any questions from the audience.
Thank you so much, Alex. We are now open for questions. As a reminder, you can raise your hand and I will unmute you, or you can type in Q&A and I will read your question for you. Okay, so if no questions, I am now handing back the mic to Warwick for our next speaker. Over to you, Warwick.
Thank you very much, Anna. Can you hear me this time?
Yes, we can hear you loud and clear.
Brilliant. Thank you very much. Thank you very much for that, Alex. That was really interesting and quite informative. Our next speaker is Jeff Houston. If you don't know who Jeff is, I'll be surprised. Jeff is very well known throughout the world as the chief scientist for APNIC. He's going to be talking about one of my favorite subjects at the moment, which is routing and invalid routes, and specifically about the fact that he's going to do some reviewing of measurements from the customer's perspective, the user's perspective, rather than us as the service providers. So over to you, Jeff.
Thanks indeed for that. Let me just share a desktop this time because it's always so much more fun, and flip into full screen mode. So yes, this is the title of the talk. Oh my God, it's too long. How about that? What I'm going to talk about today is actually an exercise in trying to actually measure the effectiveness of this routing security instrument, RPKI. To do that, though, it's useful to actually understand, what are we trying to do? You know, what's this objective of routing security? And to help you, because I know it's a tough question, I've given you a few answers. Now, if you're just going to pick one, which would you pick? Is it to protect everyone else from the fact that I've got fat fingers and I have operator mishaps? Or is it just going to protect us from some of my fat finger problems? Well, maybe it's going to protect the routing system from nasty folk who are trying to hijack routes. Do we really think it's going to work with all of them? Or maybe we're just interested in bogus address prefixes and stop them being moved around. As you see, there's a whole bunch of subtly different objectives that we could say, yes, routing security should do that. But if I asked you, what's important? What would be your answer? Now, we can't secure routing completely. If we really wanted to make sure that the entire routing system didn't carry routes that we didn't intend, so it was protocol-wise accurate and policy-wise accurate, then I'm sorry, you're on another planet. We don't do that. We can't do that with BGP. Oddly enough, BGP is a non-deterministic algorithm. See the footnote down below. You know, what we actually get is BGP is a negotiation protocol, and we actually can't predict in advance where it's going to go. So if you want to sort of make completely clean BGP, then I'm sorry, that isn't going to happen. So we've got a slightly modified goal of routing security, which is don't promote lies. And so this whole issue about route origin validation is designed to prevent BGP speakers from learning synthetic non-truths, routes that aren't authorized by the holder. Now, what's going on is don't steer users down bad paths. Don't misdirect users. So that can actually give us a clue to what the real objective of routing security is actually all about. Because it's actually not about BGP, the protocol. It's not. It's actually about users. It's all about users. And it's down the bottom. It's protect the users from being directed along bogus paths to stop them going to places that you never intended them to go to. So with that in mind, can we measure it? Can we actually look at the system and go, wow, how many folk are being protected? So maybe what we could do is, instead of looking at the number of people who are protected, maybe we look at the number of people who can be misled. So if I deliberately push out a route that is invalid, it's wrong, and you know, I did it to myself happily, maybe we can count the number of users who get misled, because that actually gives us a feel as to how effective RPKI is in reality. How much of the user base out there is actually going to get protected when a deliberately falsified route, through malicious purposes, fat fingers, or any other kind of reason, but when a bad route gets propagated, how many folk get to learn it, and how many folk have their traffic follow that bad route? So we could take that measurement and do a snapshot. You know, here's a picture, X%. Well, wonderful. But in some ways, what we'd like to see, as with all of these evolving and new technologies, all of these technologies which are kind of up and to the right, we'd actually like to see what happens over time, what the evolving picture is. What does it look like tomorrow, the day after? What are we doing in terms of gradual piecemeal deployment of this idea of route origin validation on the internet? So that's the objective here, to try and actually look at the impact of invalid routing on users over a long period of time. So what's the measurement approach? What are we doing inside the lab to actually do that? So if we're looking at the effectiveness of this secure routing system to stop folk having traffic directed along bad paths, then that actually gives us a clue to what the measurement's going to be. We set up a bad path, and we make sure that, oddly enough, the only way to get to the destination is to actually follow a path that's invalid. And by invalid, what I mean is that the RPKI, route origin validation, that mouthful, yields an invalid answer. It's well signed, but it's the wrong AS. It's not an authorized AS. So that announcement is bad. And what we then want to do is actually get a large set of users from across the entire internet to try and reach web server, and actually see it's not one, web servers located behind this bad prefix. And just to make sure we understand what we're measuring, we need a control. We need a control of a valid path going oddly enough to much the same destination, and compare the control against the invalid. Measure and compare. Now, let's just go quickly through the methodology to do this. I used Krill. If you haven't used Krill, you should look at Krill. Krill is really cool. Krill just goes set up, run. Amazing. There's a URL down there. Have a look at it, set it up and run it. So what we did was get a prefix from our local friendly RIR. Thank you, APNIC, one of the research prefixes. And we took one of the research autonomous system numbers and actually set up our own RPKI repository as a delegated instance. So we're not running hosted, we're actually running our own RPKI repository and advertising a set of rowers about that prefix. So that's step one. Interestingly, even that gives us an insight on the uptake of RPKI. Because if you're running some kind of validator, you actually have to go and look at every single repository of RPKI information, often, all the time. And so if I am one of these repositories, every relying party, everyone who's doing this job comes to see me. They come and visit once a day, twice a day, whatever. So what I've done, and that's, I suppose, the first really simple one, is to look at the number of unique IP addresses every day. And that's the count here. And I've actually broken it up into the two different kinds of synchronization protocols. We started doing this in March, so there's around 6 months of data. We started with around 800 unique IP addresses. Don't forget, 4 and 6 aren't matched properly. So the real number might be something lower, and some folk are coming in 4, some folk are coming in 6, whatever. But notice that around mid-May, rsync fell way out of vogue, which is a good thing because rsync's really slow. And RRDP, the HTTP-based synchronization protocol, gained a massive amount of favor and a whole bunch of new users. So in 6 months, the number of clients has actually doubled. But what I really find fascinating is that there are more clients on weekdays than weekends. I'm like, does bad routing not happen on a weekend? I'm like, what's going on? Why is the weekend number lower than the weekday number? Cron doesn't take any time off. Last I knew, my laptop machine, my machines don't take time off. So why does this have a weekday weekend pattern? The mysteries of the internet. If anyone has an answer, keen to know. And why is it more obvious in RRDP, the HTTP protocol, and a lot less obvious in rsync? I have no answer. Anyway, onto the methodology again. I said I wanted a control, and there's 2 ways to do a control. One is you actually have the 2 running in parallel. But the other way is to actually flip states and have the control and then the measurement and then the control and then the measurement on the same prefix. And so what we did was actually set up a state that flips. And those are the cron tab entries where we actually flip the state from good to bad to good and so on, just using precisely those entries. We'll talk about what we found about that in a second, but let's just follow a bit further. Critical points of failure, resilience. We thought to get a big picture, we actually need to get this prefix and AS advertised in multiple locations. So to start, we're using Los Angeles, Frankfurt, and Singapore. We're interested in getting a few more, and we're using 3 different transit providers, 3 different hosting providers. Now, there's not much there. It just delivers a 1-by-1 pixel. But of course, I'm also got the prefix and the AS routing in BGP. So I actually needed a hosting provider that actually did BGP. Because of those first limitations, interestingly, V6 is not everywhere, not in the hosting world. So it's V4 only. Yeah, but you know, you go with what you got. And then what we did was load up a unique URL that maps that destination into a measurement script. And so this is all HTTPS, unique DNS label. We try and get rid of all parts of caching. You can only get this URL if you actually go to it. There is no caching going on whatsoever. And then feed it into the ad network. We use ad-based measurements. I'm pretty sure most of you have heard of this by now. We get around 10 million ads per day. And what that gives us is a massive cross-section of the eyeballs of the internet, because the ad system is truly one of the marvels of the 21st century. It's glorious in every possible way. Ads are brilliant. Thank you, everyone. And then we collect and analyze this data. There are a lot of zombies and stalkers out there, so we do make a lot of effort to try and make sure that we're getting current experiments. Around half of the DNS traffic is actually zombie traffic, and about a third of the web traffic is actually zombie traffic as well. So in some case, trying to find the user and sifting out all the log replayers, all the stalkers, all the zombiers out from that, which actually give you false levels of answer for one reason or another, because that's not the actual eyeball you're tracking anymore. It's just something else. Don't ever let programmers be creative. It's a bad idea. And that's why standards are so good. Standards stop creativity. The reason why I say this is when we started to flip these row states from good to bad, we were kind of wondering what the right frequency was. Because if I have a prefix that's good and I want to turn it to bad, how long should I keep it bad before I can turn it back to good again? How long does it take for the routing system to learn a change of validity state? And does it differ from good to bad and bad to good? Good question. Now, in some ways, this is easy to do in Krill or anything else. So what actually happens down at my side is when I flip the validity state, I revoke the previous end entity certificate. That's a bad certificate. Do not use it, and publish a new one and a new rower. Here's the new state. So the crypto state is always good. It just happens to reflect the right AS or the wrong AS. But the real question is, how often should I do this? And that actually gets down to how often do clients come along and check your status? What's the interval when folk visit you and say, what's changed? What's different in your repository? What should I learn? And one of the things that's missing in those many, many RFCs, too many, and all that verbiage, is actually a definition of what the requery interval should be. Even a clue. The original documents mumbled something about 24 hours, which is probably way too long. But since then, create programmers have become creative. Now, this is the graph of the distribution of intervals between successive visits from the same client. And what's interesting is there are a bunch of folk who come every 2 minutes. So 120 seconds is really popular. And this is actually divided up into 10-second increments, but it's a log scale. So a lot of folk come every 2 minutes, but not everyone, because there's a second peak at 10 minutes. And there's another peak at 1 hour. And if you actually look, there's trailing out up to 1 million seconds. Wow. Sort of single visitors going, oh, this RPKI stuff. And you never hear from them again. I'm also interested as to why the lag. Why are there folk with requery intervals of 7 minutes, 9 minutes? It doesn't seem like something that people programmed. It seems like something in the system. This kind of lag that's going on in between those three popular intervals. So here's a cumulative graph so you can see what's going on. There's this sort of period from 2 minutes to 10 minutes where I see a bunch of requery intervals, and another period from 10 minutes to an hour, and then a folk at around an hour. And then there's a bunch more round about within 2 hours. 75% of clients have done their requery and checked the status. So 2 hours would seem to get most people. But why the lag? I found this over in Wikimedia. And what it says is the amount of time taken for clients to pass through the entire RPKI repository set. So if you're a client, you need to pick up from every single RPKI distributed repository publication point. How long does it take? That URL is interesting and they keep on updating it every day. But you notice that there are some lags of 27 minutes to go and fetch the state from some of these repositories. So some publication points are geologically slow. So slow that they're unusable in a real-time system. Bad move. So hopefully, if you're doing publication, you're down the bottom in a few seconds. But if you're one of these folk that Wikimedia says, wow, it takes minutes, you should look at what you're doing. It needs to be better. So what did we decide? Well, we couldn't make up our mind. So we actually used two values. And here's the 1 week schedule of valid and invalid. So for the first part of the week, we keep it up for 36 hours, down for 36 hours. And then we flip it up for 12, down for 12, and then resume 36 hours. So we move between long held and slightly shorter when we're flipping states. So we can actually see this when we look at stat.ripe.net. And if I had time, I'd go and play the BGP play. Haven't got time, go play it yourself. But lots of noise happens. Oh, hell, why not? Lots of noise happens. It all looks very dramatic. Here's a bit of it looking very dramatic. And the entire system, when I change state from valid to invalid, reconfigures for that prefix a huge amount of the routing state. Fun and games with BGP. But this is actually what I wanted to show, because this is actually the interesting bit. This is the per second fetch rate across 1 week. And when the route is valid, we don't get 100% because there's always some kind of drop. But when it's valid, it's up at around 96, 97% fetch. When it's invalid, as you see in the red, it drops down by about 15% at most, but mostly about 90% or so. But there are two interesting transitions. The transition from good to bad. And as you notice in the red, it's not immediate. How long does it take for the routing system to actually see and react to that invalidity? The major change, if I blow up that graph and look very closely, occurs at precisely 30 minutes. That's when most folk get to update their BGP and actually see the change and see the route withdrawal. They can't get there anymore. So the last ISP to withdraw, because I'm advertising in multiple points, this is Anycast, we're actually taking the amount of time for the last one to go. It's about 30 minutes or so for most users. And what about bad to good? A lot faster. It's the first to get good. So rather than half an hour, it takes exactly 5 minutes for a noticeable state change from the bad state to the good state. So interestingly, those transitions are asymmetric. 30 minutes good to bad, 5 minutes bad to good. So why are there 2, 10, and 60-minute timers out there? Meh, creativity. I think 2 is way too aggressive. Whoever put in 2 is thrashing the system. And as the system grows across all of the internet, we're going to spend so much time doing thrashing. I think 60 minutes is way too slow. I'm like, same-day service in a nanosecond world is not good enough. So personally, 10 minutes works for me. I wish everyone would have done that. So now for the big answer. This is the user impact measurement of RPKI filtering on the world today since June when I started this graph. So at 16% of users, about 1 in 7 or so, that's really quite good. That's a surprisingly large impact. So 16% of users can't get to something that's bad. Where? Well, this is surprising. Africa, Australia, the Scandies, and a bit of Latin America, Northern Latin America. But Europe, well, not so much, except Switzerland. America, yeah, so. What's going on? Well, certainly we're still turning it on. And I looked at Telstra, and about on the 26th of July, they'd done a transition. And now Telstra AS1221 drops invalids. So you can see that. Other folk like Windstream in the United States, I have a bit more trouble with. They had it on, and then they seemed to pick up a transit network that gave them a path to a bad place. So it went down, and then they got rid of that. Then it went down again, and then it's back up again. So transits are very interesting in terms of dropping. I don't think Windstream are doing it themselves. They're getting transits that are doing it. And what about Lycatel in France? 60%. It's as if they've got multiple exit points, but more than that, they've got multiple exit points and internal partitioning of the network. Because you'd expect in this kind of system, you'd either get close to 90 or close to 0. But 60%, a few folk can get to invalids inside that network, but most can't. What is going on? So fascinating. So of and all, we see two kinds of factors. There are folk, transit networks, who simply do route filtering. So CCOM, AT&T's AS7018, every day, basically 100%. So there are networks that actually don't learn invalids and don't tell their customers invalids. They filter all the time. But there are other networks that don't do it themselves, but their customers are transits that do. Now, in both cases, the objective is achieved, but in different ways. So this actually leads us to some sort of areas where we can go further. Maybe we should be doing selective trace routes to try and identify those networks where they're actually performing drop and identifying the customers that are being collected from that. And should we also look at the routing updates and do more analysis to get the same information? Some questions to think about, and there's a BOF coming up on RPKI security. Does everyone have to filter? Or should only transits need to filter? Because if you're a stub and your transit's filtering or your exchange is filtering, maybe that's enough. Why should I perform my own filtering if I'm a stub? And perhaps rather than filtering incomings, maybe you should filter just your outgoings. If it's fat fingers you're trying to solve, then maybe protecting others from your fat fingers is perhaps the best thing to do and the easiest thing to do than try and protect yourself as a stub from the mishaps of others. Maybe transit should do that for you. And then there are some deeper questions about if this is routing protection, then what are we actually trying to protect? From whom and why? Don't forget, we're only doing origination validation at the moment. Hijacking is still insanely easy by basically faking the path. So in some ways, it's not clear exactly what the protection mechanism is so far. We need to do more. And the other thing is, if this is a user protection mechanism, then it's actually not necessary for everyone to go through this effort. A stub should generate ROAs for its own routes, but quite frankly, your transits and IXs should perhaps be doing all the drop invalids. There's really not much benefit in doing it for yourself in terms of the larger internet. It's the transits and the IXs that are actually on the critical path here. So we've got a couple of seconds for questions. I'll happily turn it back over to Warwick and the MC and see if there's anyone who's got any questions. But don't forget, there is an RPKI BOF coming up. Someone can tell me when, and maybe that's a really good place to discuss this at length. Thank you very much.
Thank you so much, Jeff. We already have a couple of questions for you. The first one is from David. Would a use case for a stub doing their own ROV be something like peering IX connectivity?
It'd be good if the peering IX did it as well, but on the basis that if it's a bit like source route filtering, where you're trying to eliminate effectively source route lying from your outgoing packets. If you actually filter what you say as distinct from what you learn, then no one else is going to get infected by your accidental route drops. Now, we've concentrated a lot on incoming advertisement filtering in RPKI, but maybe self-protection and making sure that no one else learns your fat finger mistakes is of equal benefit inside all of this system.
We have another one from Chehu. What if a stub network has a lot of, say, more than 50 direct bilateral peering connection with local and overseas peers, and that might mean it cannot just rely on its transit providers to do invalid route filtering?
Well, this is kind of this interesting point of to what extent are you exposed to many as distinct from few? And certainly what we see in most routes on the internet, the interconnectivity mesh is thankfully quite sparse. Now, if you've got 50 peers, then you've got your hands full. That's a lot of work. And I don't think there are any short ways through. But thankfully, when we look at the routing system, the vast majority of those 60,000 stub networks only have 1 or 2 upstreams. And so the case that Chehu mentions, 50 or 60, yes, you got a lot of work. You've got a huge amount of work. Nothing can help you. But if you've only got 1 or 2 transits, then perhaps it's better to actually look at their filtering state and aim default at them and rely on them to do the filtering for you. You don't have to pedal your bicycle all the time, particularly if your own topology is much more constrained than that.
Okay, we have a comment from Aftab. Australian results, or regarding Australian results, stats mentioned Lino this filter, but contrary to that, I could reach an invalid prefix from them. Probably I'm missing something in that data. So would you like to comment about that?
Well, in my particular case, I use 3 different transit networks in 3 locations. And you can, as long as you can get to one of them, you're not counted as filtering because you've got to filter invalids no matter how you learn them. So the issue was, it was a deliberately difficult test. The other part of this, which we're actually not sure about myself, is to what extent the withdrawal propagation of an invalid route occurs quickly or not. Now, withdrawal itself is a fascinating BGP question, Aftab. We learned in the V6 network, well, about 5 years ago, that all of a sudden there were these ghosts in the network, that the original announcement had been withdrawn, but not everyone had learned of that withdrawal and was still actually had learned the route that had disappeared from years ago. Now, we know that there are ghosts in V6 because at the time, the network was small enough, we knew every route. There are 800,000 odd routes in V4. We actually don't know which are the ghosts and which aren't. What is real and what is just bad BGP state that's never been flushed. So the other explanation about this is, BGP, is not exactly accurate all of the time, which is itself a fascinating area of study.
Okay, I'm going to ask the last question. This one is from Tim. Do you see an issue of RPKI ROA convergence where more and more ASNs adopt delegated RPKI, thus increasing the number of places a network has to scrape ROA state from?
In its worst case, this becomes a massive problem. If there are 60,000 or 100,000 separate RPKI repository publication points and 100,000 clients, and all those 100,000 people are asking 100,000 sites every 120 seconds, then we're going to be consuming a lot of network a lot of the time, and your repository hardware is going to be running awfully hot. The system as it stands can't scale to that level. So design trade-offs are already happening and will continue to happen. We're using hosted publication points where a whole bunch of information RPKI is picked up in the same repository point. That's actually a good thing. I talked about the timers that you use to sort of refresh your information. I think 120 seconds is actually quite aggressive. And I think if we lower our expectations of responsiveness and look at 10-minute query intervals, because in practice, the time to actually reflect the change is, as I said, between 5 minutes and 30 minutes. So if we dropped that requery interval, we actually get a whole lot of space back out of the system and we can grow without melting it. But yeah, no, it's a problem. If we go down the path that everyone publishes and everyone looks at everyone else, that's a lot of data. And how we cope with that in the longer term is a really good question. Thank you.
Thank you so much, Jeff. I am now handing back the mic to Warwick to close the session.
Thank you very much, everybody. Jeff, that was a really good session as usual. And I look forward to having further chats with you about this as we go forward with this, given the situations around the world. From myself, I just wish to thank Jeff and Alex for their presentations. It's been fantastic this morning. Oh, sorry, this morning for me, this afternoon for some of you. And I hope you all have a great day. Thank you very much for attending this session.